So in this problem, we begin from rest and we release the system. And after a short time, this box is moving downwards with velocity v1, and this box is moving upwards with velocity v2. That all okay? We're also told that this separation distance is h. And so my problem has to be in terms of h. So it comes down to. I need a way of expressing what's happening here. And when I look clearly at this problem, it looks to me like box 1 descends some distance while box 2 ascends some distance. So I'm just going to kind of call this box 1 and box 2. Is that okay for you guys? And I also need to, I don't know, I need to make some reference. So this blue line represents where the boxes were at time 0, at state 1. So box 2 goes up a distance h2, while box 1 descends a distance h1. Now, when I compare state 1 to state 2, I'm trying to determine which box has kinetic energy, which box has potential energy, all that kind of stuff. So each box can be graded by its ability to have potential energy and kinetic energy at each one of these states. So although I'm writing it in there, you know, the idea here is just to assess, does the box have kinetic energy? Does it have potential energy? I think we can start by saying that there's no kinetic energy at the start of the question. I can cancel both of those out at state 1. Is that okay? Box 1 is above its lowest position. So box 1 does have gravitational potential energy at the start of this problem. Box 2 is at its lowest position. So it does not have gravitational potential energy at the start of this problem. I'm using that blue line as my reference line. When I go to state 2, both boxes have kinetic energy. No argument there. But box 1 is now at its lowest position. It has exhausted its gravitational potential energy. Box 2, on the other hand, is above the lowest point it was going to be at. So it has acquired gravitational potential energy. So if this is a conservation of energy question, and I believe that there's been no outside force to take energy away, the gravitational potential energy for box 1 is going to have to be equal to the kinetic energy of box 1 plus the kinetic energy of box 2 plus the gravitational potential energy of box 2. That's the conservation of energy portion of this. And with the symbology I've chosen to use, this will be mgh1 equals 1/2 mv1 squared plus 1/2 mv2 squared plus mgh2. Any questions about any of that? Yes, sir. I don't believe the system is losing energy. Why do you believe that?
I'm saying that because for box 1, it's losing gravitational energy.
Okay, box 1 is losing gravitational potential energy. Gravity is doing work on box 1, yes.
Isn't the rope also doing work on it? So the gravitational potential energy would not be the only contributing factor to velocity change?
Although what you're saying is not untrue, it doesn't factor into us discussing conservation of energy. You see, what you're suggesting has been I'm sorry, for you guys at home who didn't hear this, they're saying, isn't the tension in the cable also doing work on box 1? This is coming to us from Kyle. So, you know, but the thing to think about here is what Kyle's trying to indicate is that when we dealt with forces, we talked specifically about how when we deal with the acceleration of a system, we have to take both forces into account. That would be the gravitational force and the tension. That's true. And it is true that in this case, tension is doing work on the box. And because it's doing work on the box, shouldn't it also indicate how it contributes to its change in kinetic energy? But the thing is, you'll notice we have two buckets of kinetic energy that have to be filled in the second part of the problem. If you're worried that we're not taking into account the force that's doing work on the box because of that cable, it's an unfounded worry. Because the tension in that cable is doing work also on box 2, changing its kinetic energy. Correct? So although there is tension in the cable, what you, I think, fail to realize is that the tension that's in the cable is due to the fact that gravity is acting on box 1 and box 2. That creates the tension in the cable. It connects these objects together. It also helps transfer the energy from one object to another. It is doing work. But conservation of energy never asks us how much work is being done by individual forces acting on the object. Never has an object slid down a ramp and us asked how much work was done by the normal force on the box as it slid down the ramp, nor how much work was done by the component of this weight acting down the ramp as it slid down the ramp. We merely looked at the change in height of the box and were able to use that directly to indicate how much the kinetic energy changed. And the reason for this is we're absorbing all of that into our idea that the total energy of the system is remaining constant. We're absorbing these internal forces which act in two different directions on two different objects and saying that the inertia of the system will be internally kept inside the kinetic energy and the gravitational work done on the system will be kept inside the gravitational potential energy. And so we do not have to calculate any work done by the tension in the cable since it's going to be considered an internal force to the system. Okay? Now, if you want, and you're not looking at me, so I'll wait, but if you want, you can determine how much the tension force is in terms of the weight of the boxes, and then calculate the work done by tension on each of the parts of this system. It will still work out. I don't want to do that, but I'm willing to let you do it. Okay? And it's not a terrible exercise. I would start with a simpler system though. Okay, so what we have to do now is we have to find a way of expressing this in terms of one velocity and h. We can make it the velocity of one of the blocks. It doesn't matter. So we could solve for v1 or v2, or we could solve for h. But this whole thing has to be in terms of capital H, which I hope you realize is equal to h1 plus h2. Right? That has to be true. Now, if you want to solve this problem, you're going to have to do more. And the thing that you're going to have to do is you're going to have to recognize that h1 equals 2 times h2. Now, I don't know if you can put that together as to why that has to be true. But I think we should be able to deduce that because the cable is doubled up around box 2, that if box 1 goes down a meter, box 2 goes up half a meter. That's how much of the cable has been retracted. At the same time, that instantly means V1 equals 2 times V2. So that suggests we can do some substitution here. And that's the first thing I would do. I would substitute in H2 and V2 for H1 and V1. So let's make that happen. That's going to shove it over there and rewrite it out. And we get M. Can I just go ahead and cancel out all the M's? You guys are good with that, right? So G times 2H2 equals 1/2 times V1 is now 2V2. So 2V2 squared plus 1/2 V2 squared plus, this can be GH2. Now, I'm also going to point out right here that if H1 equals 2H2, then this equals 3H2. That okay? You guys see why that has to be true? That's good because I can't have it in terms of H2. I have to have it in terms of capital H. So although I'm going to subtract this from both sides and get GH2, I'm really going to write this as GH over 3. Everybody follow that math okay? No, it's a lot in once. If you're asleep, you're not going to see it. But it's it was me subtracting GH2 from both sides and then substituting. All right. And that's going to equal, let's see, 2 squared is 4. So that's going to be 2 V2 squared plus a half of V2 squared. Is that 5 halves? V2 squared. Now we're solving this in terms of V2. It doesn't really matter. Once we get this, we can get V1 at the same time. So all we have to do now is solve for V2. And that part's pretty straightforward. So I think I can leave that here and say that you guys could probably get that. But you should have 2 answers. You should have V2 squared equals, what's this? 2GH over 15. And you take the root. So I'm doing this because I have a few people who are making that face. And so there. If that's V2, if I want to get V1, it's just 2 times that. Interesting, maybe. I like this question. But once you know to do this, this question kind of, becomes a little bit less interesting. But is this testable? I think it'd be interesting to figure out what the tension is in the cable in terms of the masses. I do think that would actually be an interesting question. So just so you know, I would love to follow up because I think this is a good force question and a good energy question. And I don't think it's obvious what that tension in the cable is going to be. So that's why I'd like to, I would work that out. So if I were you, that'd be a good experience for you. And that's the tension in that cable is going to be constant. So I would just figure out, somewhere in between this, some way of expressing this, you'll get your acceleration and all that kind of garbage. But box 2 and box 1 have a related acceleration that A1 is going to have to equal 2 times A2. That still has to be true as well. So if you want to find the tension, you'll have to do that. That's how you'll get to it. All right. I like this one. It's a good question. It was interesting. I saw it in the back of a book and I liked it. Yes, sir.
Why is the total energy of the system equal to the gravitational potential energy of Block 1?
Luck?
Block 1.
No, I said luck. No, I don't know, because it's the only thing that has energy at the start of the system. Do you see any other place where energy seems to be inside the system beforehand? It does. But it doesn't have any, it doesn't contribute any gravitational potential energy to the system because it's going to be hoisted upwards. So it's going to start storing energy as it gets hoisted upwards. Are you sure? One of the things about the system is block 1 is the only block that technically has any gravitational potential energy because it's the only part of the system that actually goes downwards as the system operates. But all the other forms of energy that end up existing in the system after block 1 begins to descend comes from that. Now, I want to remind us that it's because block 1 is being accelerated downwards, that the unbalanced force acting on block 1 pulls it downwards, and that unbalanced force pulls block 2 upwards. That acceleration still exists. You could work this problem out with force and use motion equations to figure out what these 2 velocities are. There's absolutely no reason you couldn't do it that way. It'll work out to be exactly the same. I don't think that'd be any fun, but good luck. All right. I'm going to expect that at some point this week, probably, I'm going to be testing your abilities to kind of put these together now that we took a couple days hiatus from me doing that. So probably in a formal way, I'd say Wednesday, first 15 minutes of class, you're gonna have to demonstrate your ability to do a conservation of energy question now under duress. I've given you lots of opportunities to practice, and I've even been nice enough to give you homework just in case you want, because some people were complaining I hadn't posted the homework yet. So please make sure you're taking a look at it. But I'd say by Wednesday, I should see some progress here. Fair enough? We're going to do one of your homework questions right now because I'm such a swell guy. I don't want you to feel too stressed about having so much homework. And so I'm doing this problem because it is one of these questions that's in every single physics book. And because it is, I think we have to see it. And since it is in the back of the chapter, I had to assign it. But I know if I don't go over it a little bit, students tend to just flip out with this question. This question has been on the AP exam. It hasn't been on there in a long time because, like anything else, it's one of those questions that once you've done it once, you can probably do it anytime. And your book is nice enough to break this up into multiple parts, as they actually did on the AP exam as well. But the way this problem was taught to me was not. It was just one question. And so I like to put it to you guys as the same way it was put to me when I had to do this problem in college. Ice domes like this are things they make up north for kids to play on. Making one that's actually a hemisphere is a bad idea. We're going to see why. But an ice dome like this, the idea is you would actually etch stairs into the backside of this, and then the kids can slide off in almost any direction on the other side. Does that make sense? So you have one side where the kids climb up, and then they can just kind of fall off in all directions. And it's supposed to be fun for the kids. We'll find out why it's not particularly fun for the kids here in just a second. So let's just assume for argument's sake that this object has a radius, capital R, and is a hemispherical dome. I'd like to know when they fly off the dome. At what angle? Assume we measure our angles relative to the top and that the kid's going to make it to some point over here. I'd like to know at what angle the kid no longer is in uniform circular motion and flies off the dome. Because that's exactly what's going to happen. Now, you might not know where to start that problem. That's too bad, because that's how it was put to me, and I just had to do it. But I'll be kinder. Let's start by you finding out how fast the person is going in terms of theta. You can have R in your answer. You can have G in your answer. They're going to start at the top, and they're going to begin to slide. No friction. Just tell me what their velocity is right here as a function of theta. Okay? Give it a shot. Talk to people at your desk. This will take you a few minutes, but I am asking you a conservation of energy question, if you haven't figured that out yet. So we're going to... All right. Well, most people are back. So some folks still left out there in their breakout room. You guys who are back, did you guys find an expression for V? All right, excellent, excellent. Devon also did. So Devon, why don't you tell me how you did it? Because you're excited to tell us.
I'm not excited, but I can tell you.
Well, I'm excited for you to tell us.
All right. So I started with the energies and I made two pictures, one before and one after.
Okay, so just so I can repeat, because I can't hear you from back there.
Yeah.
Devon said he started with the energies. He made two pictures. I'm not going to make two different pictures, but okay. So I assume we're talking about this position and this position, true? Can you tell me about the energy at each of those two positions?
So at the start, I just had the gravitational potential energy.
All right. So how'd you said this is just gravitational. Great.
And then for the second one, I had the potential energy, or the gravitational potential energy plus the kinetic energy that is not as low.
Okay. So where are you taking your lowest point to be then?
I took the lowest point to be the ground.
Perfect. That's fine. That's fine. You don't have to do it that way. I just want people to know that you could make this your lowest point if you wanted, but your lowest point is always changing then. It's not a big deal. But what did you use then for your initial gravitational potential energy?
For my initial gravitational potential energy, I had MgH1, but I substituted H1 for R.
Excellent. And then what did you have for your gravitational potential energy afterwards?
For afterwards, I just had the MV and substitute that.
Okay, so you said this was H2?
Yeah.
All right. So this is H2, right?
I see where I could have substituted that.
All right, let's see if somebody at home can tell us what should we substitute in for H2? I'm looking to see if somebody at home can tell us. Joey can tell us. Justin can tell us. Justin, why don't you tell me what you got? I heard from Joey earlier today. A lot.
R cosine theta.
Excellent, that's right. So this is going to be R cosine theta based on the way we're measuring theta. There's going to be at least one of you is going to ask, but this is also theta, which is why it's R cosine theta, because this is R. So that'll make this R cosine theta. So the last thing to do is just drop in 1/2 mv squared, right, Devon?
Yep.
And set those equal to each other. Now, you're just going to solve for the velocity here, but I hope you see first, you can cancel all those m's. And notice that when you do this, you're going to get gr times 1 minus cosine theta. That shouldn't be too big a surprise. That would have been what would happen if you had found this distance out directly. Right there. Right, we would have used that same thing from earlier in the year because it's still round. So we would have gotten that same change in height with that 1 minus cosine theta thing. Either way, this has to equal 1/2 v squared. So let's just sit on that for a minute. I don't think we actually have to get it in terms of v. But any questions to this point? Now, if we want to figure out where they leave the surface of the ice, well, then I think we've got ourselves a centripetal force problem on our hands. Why don't you draw yourself a free body diagram? I think you're going to need it. And we're looking at the free body diagram at this point. We're going to say this is the point where they leave the ice. We know how fast they're going now. What's a free body diagram going to look like right there? Give it a second, then I'm going to pick on one of you to help me out draw that. What time does the bell ring? I want to make sure we're on target. How many? 3 minutes. We got to hurry then. So Xavier's already done because he's just looking at me like I already did that. So Xavier, why don't you tell me how to draw my free body diagram?
You put an arrow downwards.
An arrow downwards. Okay. So my dot's right there. Arrows straight downwards. Fantastic. What else?
That's good if he's not in contact.
Oh, we're going to need more than that. Let's go ahead and put that normal force in, just like he is in contact.
And you can put the normal force up and to the right,
All right.
perpendicular to or parallel to R, like in that direction. And the theta's going to be next to the vertical axis.
All right. So normal force has to lie along a radial, and mg is going to be straight down. Any question about that? That's important. Yes, sir.
Why would you draw the vector for the normal force if you're saying it's 1 ev?
Because I need to impart something to people who don't see this. Now, yeah, I agree. We are going to look for the point where the normal force goes to 0. That part's true. But until the normal force goes to 0, there are people who don't realize that the normal force is going to be along a radial. That when I try to look at this, because the next thing we have to do in determining this correctly is to establish our coordinate system. And unless you really know what you're doing here, you might feel inclined to establish your coordinate system aligned with the weight, but that would be wrong. You want to establish your coordinate system aligned with the normal force. You want this to be the y direction, and then you want this to be the x direction. And actually, you want that to be negative y and this way to be positive y. And the reason is very straightforward, and I want to remind you of why. There has to be an acceleration towards the center. We need to align our coordinate system with the direction of the acceleration. There are two accelerations here, though. There's a radial acceleration that's causing the circular motion, and there's a tangential acceleration that's causing an increase in the velocity. And although we could argue that there's only one, no, they are two, and we are lining up our coordinate system specifically so that we can state that the net force in the y direction is equal to mv squared over capital R. We need that because this is what's going to tell us where they leave the ice. Now, you have everything you need to be able to figure out what this angle is going to be. So try and come in tomorrow knowing what the angle is. You're just going to be combining the things that are here. All right, folks, that's all there is. We have that short class on Monday. Nobody's upset about that. So you guys at home, see you later. This was real and it was fun. If you're coming back for after school, I look forward to seeing you. All right, go ahead, Sana. What you got?
Did you see my remind message by any chance?
No. When did you send it?
I think right before lunch.
Then not just no, but heck no. So let me see real quick. Why don't you show up after school so you can see what I'm going to be doing instead of retakes?
Okay.
Okay? It'll only take about 5 minutes.
All right, deal.
All right, see you then.
Okay. Bye. Thank you.
You're welcome. Bye.